Hi everyone. I'm going to talk about streaming to scale real-time infrastructure for AI. So I'm Aravind. I lead the real-time infra team at OpenAI. Prior to this, I was at Uber. We led infrastructure efforts there. So I'm going to share our journey of how we built the streaming infrastructure stack at OpenAI, what are the challenges we faced, what are the different iterations that our architecture, what are the different iterations we did, and how successful it was. So before going further, let's talk about why we even need real-time streams for AI. By the way, I'm reusing some of my slides from the keynote earlier, just to set context. But after that, yes, it'll be a technical deep dive. So let's talk about why we need real-time streams. So there are a bunch of use cases at OpenAI that needs this. An example is data flywheel. Now, what is data flywheel? Data flywheel is a self-reinforcing loop where, let's say you build AI products and systems, and you launch them. Now you get a lot of product usage data. Now, based on the data, you end up using that insights to train better models. And eventually, when models become better, that drives AI products and usage even further. And this flywheel keeps spinning. Now, the reason it keeps spinning, that's streaming infrastructure. All critical events from product usage kind of flow through Kafka as the durable store. And whatever processing that is done on top, it's either Kafka consumers or Flink jobs, which do a lot of aggregations, joins, transformations, and whatnot. Now, streaming infrastructure keeps flywheel from spinning. All kinds of user inputs like which response do you like over the other. In some cases, you would see ChatGPT with 2 responses. Those kinds of user inputs are very valuable for us to train models that are more personalized to your use case. Another example is experimentation. In today's AI world, AI experimentation, it's kind of very important for model progress. And in today's world, experimentation is more around model training is highly asynchronous, it's distributed, and there is, so the real problem here is if you run an experiment at a large scale, how do you even know what the latest state of that experiment is? That involves you pulling information from multiple sources, joining them, aggregating them, grouping them with the right keys, and then looking at, is this experiment going well or not? Now, stream infrastructure, if you do not have a good solid stream infrastructure, we have seen engineers and researchers build their own custom bespoke tooling to solve all of these problems. But once you have a reliable streaming infrastructure, it ends up making their lives a lot easier. So what we do at OpenAI is all of the experiment metrics and usage kind of flows through Kafka. All of the aggregation systems is built on top of Flink. This enables all researchers and engineers to basically understand where an experiment is going and what the right next steps are. This is just a sneak peek into the different types of use cases at OpenAI where stream infrastructure is used. Let's go back in time and see where all of this started, how streaming infrastructure at OpenAI was, let's say, in 1.5 years back. And we'll go back in time, then we'll try to look at the problems then we'll start designing the stream infrastructure stack step by step until we come back to this day, and then we'll talk about it. That's basically what the talk is going to be. So how it all began? We're going back in time to early 2024. There was a strong user demand for streaming infrastructure. People wanted Kafka. People wanted to publish events. People wanted to do a lot of asynchronous processing. When I say people or users here, it's all about all the internal users at OpenAI, all product teams, research teams who want to use stream infra. We also had a lot of use cases around data lake ingestion, like ingesting data from Kafka into the warehouse for a longer retention and doing a lot of analytics on it. But early 2024, the platform was very scrappy, and it was in very early stages. We had a few rough edges. Number one, there were no standardized Kafka clusters. There was user teams kind of spun up their own Kafka clusters whenever they wanted. And there was a lot of confusion around, do I spin up a new cluster, or should I just add a new topic to an existing cluster? And every team ended up spinning up clusters in its own way and things like that. So there was no standardization. The second thing is, Kafka was a single point of failure. It's a fair ask to have the entire stream infrastructure stack to be tolerant to a single region failure. And we did not have that. So Kafka was a single point of failure. The third thing is there were a lot of scalability limitations in our current setup. An example is basically, OpenAI, as it's true for a lot of AI development today, a lot of development happens in Python. Now, if you end up using Python a lot, you will end up, due to overcome GIL problems, you will end up having more processes instead of threads, which means all your systems like databases, Kafka brokers, end up having a lot more connections from it. Now, we end up having a lot more connections that has its own set of scalability problems, and we faced a lot of that too. There was a background noise of failures due to Kafka, in Kafka published errors throughout. So this is how early 2024 was for us. So how did we solve it? If you were to solve this problem, I see a few different ideas coming up. Like either you spin up stretch Kafka clusters, or you spin up different Kafka clusters and mirror or replicate data and things like that. But what we actually identified was, we noticed that there are some trade-offs that we could make. Maybe you say no to ordering. You say no to partitioning. And that was true at OpenAI. Most use cases do not need ordering or partitioning. And taking some of those trade-offs, maybe we build a much simpler infrastructure and also something that is simple for our users to use. So that's exactly what we did. The solution started off with building a bunch of proxies. So the first thing that we did is, Kafka was a single point of failure. So okay, fine. How do we solve it? Let's spin up multiple Kafka clusters. Sure, you have multiple Kafka clusters. Let's say instead of one cluster, you have 3 clusters now. What do you do now? Do you want your user teams to talk directly to all clusters? Maybe not. Have a layer in between. Let's add a proxy. So we spun up a producer-side proxy. And then eventually we added a consumer-side proxy too. And then our architecture evolved from that, right? One question that we asked ourselves at this point is, what are the guarantees that we're going to give? So if a Kafka cluster goes down, what do we prioritize? We said the thing to prioritize is basically to keep the lights on. If a Kafka cluster goes down, make sure at least new publishes to the topic. We are going to support that. How do you retrieve the old data from the cluster that went down? Let's keep that out of scope. So no replication, no durable things on top of the data that is already there in Kafka. This was something that we treated as out of scope for the first version. So what we ended up building? We ended up building a producer-side proxy. We call the proxy Prism, and we call the client Photon. So, and what the proxy does is it basically load balances, publishes onto multiple Kafka clusters. Now, you could ask, oh, okay, are you throwing out ordering? How does partitioning work and things like that? The answer to that is yes. There are a bunch of trade-offs we are making. I'll talk about that in a bit. One key feature about this is it has circuit breakers built in. So let's say a Kafka cluster goes down, Prism detects that and ensures that no messages go to that cluster, and it kind of gets load balanced across the remaining clusters that it has. Also, the implementation-wise, it's actually very simple. It's just one gRPC endpoint which exposes produce batch. So you have an API to produce a batch of messages. And since you have a proxy now in between, there are fewer connections to Kafka brokers. Services can just directly talk to the proxy, and the proxy is the only thing that connects to the Kafka brokers ultimately. So let's look at how the architecture is. So you have producers that end up using the client and that talk to the proxy, and the proxy ends up talking to all the Kafka clusters. Now the proxy, at least when it comes to the deployment, we deploy Prism in all clusters where services are deployed. So the handshake between services to Prism is all local to that particular kube cluster or kube region, right? Let's talk a little bit about the consumption side. Okay, you can produce all these messages. How are they going to get consumed? The story is a little bit similar there, but we did not build the proxy here. We adopted something from open source. We adopted Uber's uForwarder. It was built at Uber, battle-tested, open-sourced. But it had a few key changes in how you consume things from Kafka. An example is, instead of services pulling messages from Kafka, uForwarder does that pull for you. And it flips the paradigm from pull to push. So services actually end up getting messages via pushes from the uForwarder service. And also, these services, let's call them receivers. Receivers can basically acknowledge a message, or they can fail a message saying that, hey, I cannot process this. And you can also say that, mark this for retry, some other pod will process it later and things like that. And UForwarder understands all these semantics. So basically, it has inbuilt retry queues. So if a message is marked for retry or failed for some time, it pushes that into a separate retry queue. You can stack how many ever retry queues you want, depending on how many times you want to do retries. And once retries get exhausted, it kind of pushes it into a DL queue. And DL queue data is kind of ingested into the data warehouse for people to inspect, like poison pill messages or any kind of data corruption in bit flips and things like that. And people can choose whether to replay those messages or not. A couple of other benefits that we get from this is it mitigates head-of-line blocking because it has all these retry semantics and things like that. So eventually, consumers will catch up and they'll move forward. Bad messages will get disregarded. And another key thing to note is, due to this kind of setup, the amount of consumer parallelism that you get is more than the number of Kafka partitions. Because we have noticed a few use cases where the rate of production is high enough that on the consumption side, if the time to process a message is kind of long, and in those cases, it makes sense for us to have more parallelism by just using eForwarder instead of just increasing the number of Kafka partitions. Another thing, architecturally, this was a little bit simpler because most of the uForwarder stuff is stateless. State is maintained in a few different places like internal components like controller, but the consumer group offsets, all of that is stored in Kafka itself, right? Another thing to note down here is when we added Prism into the stack, it is deployed in the region where services are deployed, right? So we did not add a new failure mode for single region fault tolerance. However, for uForwarder, we need to do something there. So we have deployed this in an active-passive setup so that you can do manual failovers whenever you want. Let's say this is deployed in US West. We have a copy in US East. If US West goes down, we do a manual failover and things like that. So based on all these principles, accepting all these trade-offs, this is how the consumer-side architecture looked like. You basically have Kafka clusters that flow to uForwarder, and then Kafka consumers basically consume that via a push mechanism. To sum it all up, let's put it into one diagram. So you basically have producers that talk to Photon, that talk to Prism, to Kafka clusters, to the consumer-side proxy, to end consumer services. I'm going to keep adding more components to this, but this kind of sets the stage for version 1 of stream infrastructure at OpenAI. So we'll see how this architecture evolves. One thing that I missed talking about is what about new Kafka topics? Like we just spoke about if you have a topic, sure, you can do all these publishing and consumption. That is when we introduce a new component called Lightshow. So Lightshow is basically a Kafka control plane. Right now, the state is basically all of the topic configurations are checked in to source control through a declarative file in a YAML format. And based on that, we have a lot of actions post-merge that end up provisioning the topic for you, figuring out the right cluster, and things like that. And now, so Lightshow is going to handle all the provisioning stuff for you, which means it's easy for you to basically spin up topics, spin up clusters, and then you can just start writing producers and consumers. But there are a few trade-offs. Let's talk about that. We threw away partitioning. There is no partitioning in this design. Why? Because Prism does not support that API, sure. You could publish it to Kafka, let's say. Even if that data is there in Kafka, on the consumer side, uForwarder, we don't, it throws away the notion of partitions. It just fans out the messages across different pods and different replicas your services has. The second thing is there's no ordering here because since there is a fan out on the consumption side, the third message could get agged before the first message. And the third point is there is at least once delivery here because uForwarder can do retries. There are retries in other layers of the stack too. So it is at least once delivery by design. Now the real question is, are these trade-offs too bad? Like, are we just throwing up a lot? Probably not because most of the use cases were able to use it in just the default way of without partitioning, without ordering and stuff. But in some cases where people needed it, we had meaningful alternatives. For instance, you could partition them in the downstream. Let's say you have a downstream Flink job or a downstream Spark job. You can do the partitioning there. It does add an extra bit of latency, but that was okay for most of the use cases. And the second thing is ordering. Ordering is a hard problem in distributed systems. So the way to do this in this setup is you have a logical clock, and you stamp events with a timestamp from that clock, and then you do a downstream sort, and then you get ordered events. The third thing is it's at least once delivery. How do you solve it? Do exactly once processing on the consumer side somehow. Downstream deduplication is one idea. Idempotent processing in any way. So we had meaningful alternatives to all these trade-offs. So the real question is, did it actually work? Yes, it did. I wouldn't be here talking about it if it didn't work. It did work, and our users actually liked it. So the main reason why this was successful is because our users wanted a managed platform. Like building AI products and building AI systems is complex in its own way that they didn't want to know about another infrastructure system. So they were okay to take these trade-offs. And in exchange for that, they got ease of use. Publishing to Kafka, consuming from Kafka, processing things on top of Kafka is very simple at OpenAI. And the second thing is they get reliability wins. You get single region fault tolerance in this design instead of you spinning up your own Kafka clusters and handling failovers and all that. And the third thing is it's scalable. It's scalable by design. If the throughput doubles, we just double the number of clusters. So this is basically what happened with version 1 of Stream infrastructure. And what we noticed is this is something like users are able to accept trade-offs to use a much powerful and better platform. You could ask, does this generalize well? Maybe this is specific to OpenAI. I think some of the key principles that we learned along the way kind of generalize. Like, let's say you're powering infrastructure for a bunch of products, bunch of research, or bunch of use cases. You would always have a mix of things that are simple to solve in your infrastructure versus things that are more like power user-shaped things, right? So one thing that we always kept in mind throughout this is, at any point in this time, simple things should be simple to do in this infrastructure. But complex things should still be possible. That is why we always had meaningful alternatives for our power users, and we were able to work it out and solve all the kinds of use cases that we see at OpenAI. To sum this up, what was the state late 2024 at OpenAI? We had Kafka that scaled to support more business use cases because it was just simple to use, and the Kafka stack worked well for stateless consumption. Now you see where I'm going with it, right? It solved all of these problems, but then some use cases needed stateful stream processing, right? This is when Flink enters OpenAI. So there are a bunch of Flink. Let's talk a little bit about like how people use Flink at OpenAI. What are the feature set that we expose? We adopt PyFlink because OpenAI is Python heavy. Second, we offer both Python data stream API and the table SQL API. And we integrated with all OpenAI's tools and libraries. So you could import other OpenAI libraries that is built by another team into your Flink app. We set up the stack in this way that people can just reuse a lot of things, and that was very helpful to our users. From an implementation perspective, local state store is stored in RocksDB, and Flink checkpoints get flushed to Azure Blob Storage. And there is obviously an angle to what do you do if regions go down, right? So for that, we have resorted to doing manual failovers of Flink jobs. So we ensure that Flink clusters are kind of at least running in more than 3 regions, or at least as many as possible, and we do manual failovers whenever needed. So the deployment model looks something like this. Within a kube cluster, you basically have multiple namespaces. Within a namespace, you have the Flink operator that does reconciling of Flink deployments. We use a Flink deployment CRD here. And per namespace, there is a blob store setup. And then you basically have a notion of primary and secondary inside the blob store itself. And there are manual failovers manual knobs that we can leverage whenever we need to failover and things like that, right? So this is all about Flink stack. Let's see how this actually fits into our original architecture. So this is how it is. I just moved the U400 bit a little bit up, but this is the architecture as we saw last time. Just adding Flink apps to consume from this, does it work? It did work eventually, but there were a few challenges before we adopted Flink in this kind of setup. Number one is like Flink and multi-cluster Kafka. If you have a Kafka cluster and you have Flink apps that talk to it, sure, Flink works for that out of the box. But with this multi-cluster Kafka, your input messages end up getting partitioned, like split across different Kafka clusters. Now, how would you have your Flink app work on top of it? The second thing is there is also a dynamic list of Kafka clusters because new clusters could get created anytime. And also another thing we noticed as a problem, it's not because of the architecture itself, it's because of the scale. It's around aggressive kube rolling restarts kind of impacts like running Flink apps. Like there is a lot of art into how you deploy Flink apps at scale in Kubernetes clusters. So we started hitting that problem too. Now for solution, for the multi-cluster Kafka setup, we ended up writing custom Flink source and custom Flink sinks. And to solve for the dynamic list of Kafka clusters, we implemented a service called Flink Watchdog, which I'll talk about it in a bit. And the third thing is, for aggressive kube rolling restarts, no solution at this point in time. So we basically ended up tuning some of these knobs just to get us some time to build something long term. Let's talk about each of this in a bit. So custom Kafka source. This is an interesting point. Like in a multi-cluster Kafka setup, how would you have your Flink apps interact with that? There is an inherent trade-off between consistency and availability here. Like either your Flink app, assume this Flink app can do a lot of things like aggregating on a particular key, right? Now messages that belong to that key can be in any of these Kafka clusters. Now you focus on the correctness of the app. You want it to have consistent behavior. Then you need to rely on all the clusters being up, which means there is a question mark of what happens when that cluster goes down, how will the app behave, and things like that. But the second thing is the availability trade-off. Like, because if you do that, you kind of take a toll on availability. You will have correctness issues. You can ignore a cluster and move on, but the job might not work the way it was intended or way it was written. This is actually, there is no right answer to it because there is an obvious trade-off between those. What we have figured out as we chat with users is consistency is more important than availability. So we have a few manual knobs that help us to kind of manually intervene and fix when regions go down and stuff, but we have favored consistency over availability for Flink jobs in this kind of setup. Let's talk a little bit about the Kafka sync. The Kafka sync is simple. Instead of Flink writing to Kafka, have it write to the proxy. So you have Flink apps writing to the proxy ends up routing it to the underlying Kafka clusters. This had some amount of work, but this was a relatively simpler problem to solve. Let's talk about the Flink Watchdog. So a bunch of things here. The Kafka topology could change anytime. New clusters could get created. Existing clusters could get drained. New topics could get created. And the next minute, users would want to write a Flink app. What do you do in those cases? So Watchdog is a system that basically monitors these changes from the Kafka control plane, which is called Lightshow, and basically restarts the Flink apps whenever there is a change that impacts them. And every Flink app on startup kind of gets the up-to-date state from Lightshow, figuring out, oh, this is the topic I'm going to consume, this is the clusters I'm going to connect to, and things like that. So let's see how all of this fits into our architecture here. So there is a new component here called Flink Watchdog that basically pulls from the control plane, and it controls all the Flink apps that is deployed. This is how we rolled out Flink at OpenAI. You could say version 1 of Flink. And this was mid-2025 because it took some time to get mature. And these are the wins so far. The platform scaled. We spun up a lot more Kafka and Flink clusters. And the Kafka stack continued to work well and scale well for all the stateless consumption use cases. And then Flink solved a lot of stateful stream processing problems that we faced. But there were a few challenges. There's just a lot of clusters. It's only a matter of time that you run into it. You build a horizontally scalable system, but then a year down the line, you figure out, oh, there are just too many clusters. So this leads to a lot of problems. It leads to more user confusion. It leads to a lot of operational toil. We have noticed the number of pages that our on-call gets increased with the number of clusters. So let's talk about what's the issue with more clusters. The first thing is, the first and foremost goal of the infra team at OpenAI is to make sure product teams, research teams can run as fastly as possible with high velocity and ship great things. So it needs to be very, very simple for them. We shouldn't have any user confusion there. But more clusters cause user confusion. Users have to think where is their app running. And also, which Flink UI should I use for this particular app? Today it is, let's say, in cluster 0. Tomorrow it's moved to cluster 1, right? Another problem is it also creates a lot of problems for our platform teams. There are a lot of decisions you need to make. Oh, there is this new Flink app. In which cluster should I place this Flink app? And then after some time, you should also think about, oh, okay, if this scales, what do I even do, right? So a lot of decision problems. Another key problem that we also noticed is doing manual failovers is okay for V1, but after some point, that itself ends up being some kind of an operational toil. So we started asking ourselves the question, instead of asking, can the entire stack tolerate a regional failure, we also wanted to see if it can fail over automatically. So let's go back to the architecture diagram and let's do this exercise, walking over the different components and see which is tolerant and which is not. So the producers, Photon, Prism, they're all tolerant. Kafka clusters, there are multiple clusters. There is circuit breaker, so they are tolerant. And you have Lightshow and Flink Watchdog. These are external systems which can be moved around clusters, so they are tolerant. But uForwarder and Flink apps themselves, they are not. Due to a bunch of reasons, because the active-passive setup for uForwarder was still manual, and then Flink apps needed a lot of manual intervention. So to summarize, this is how our regional failures look like. Like Kafka production was fine, uForwarder and Flink apps did not. So there are a mix of problems here. More clusters, tolerance to regional failures. How did we solve it? Let's take it step by step. The user confusion is actually a very simple problem to solve compared to the others. What we really need is we need a UI, or at least a CLI to start with for observability and help our users. And we call that Retina, because we call events Photon, and you have Retina. So, and this is basically a UI for all operators of Kafka and Flink. Anything related to streaming, this is the one-stop shop. I can show a few screenshots of what Retina looks like. We noticed that a lot of users ended up wanting to replay messages from our DLQ'd topics. So we built a workflow that allows them to do that. And also, we noticed that there are a lot of Flink apps here. So we wanted to give a page where that kind of lists all the Flink apps. People can search through it. We can open the right UI. We also have some kind of health score that is generated per Flink app based on what is the best practices and things like that. All this was super helpful to our users, right? User confusion is solved. How do we scale the platform further? There is a lot of prior art to this. It's only a matter of time you also run into this. We need a lot of control planes to basically support all of this infrastructure. It includes everything from job placement, failovers, and any kind of KTLO operations that you do, like restoration of a Flink job from an older checkpoint, or backfilling an app in a new cluster from over the last 2 days of messages and things like that. And we need control planes or automated systems that do all of these things, and we need that for both uForwarder and Flink, right? And this is exactly what we did. This is how the architecture looked. We added a few components. We introduced a Flink control plane, which manages all the Flink apps, deployments, lifecycle, everything. Then we had a uForwarder control plane that manages everything that's around uForwarder. And we had Retina, our UI. I didn't draw the edges because it basically talks to everything, but it's the one-stop shop for Stream Infra. So to summarize, this is how the current state of Stream Infra looked like. The platform supported a wide variety of mission-critical use cases across Kafka, Flink, everything. And it scaled to OpenAI's needs. And it's somewhere around 10x every 6-7 months, so it supported two such things. The third thing is users found it simple to use. Users found it simple to use back in the days. Users still find it simple to use, and I think that is the biggest win here. To look at some numbers on the scale and adoption, this is how it is. It's used by every team at OpenAI, and we see 3x growth in Kafka every quarter, which adds up to 10x every 6-7 months. And we have over 200 stream processors at OpenAI, including Flink apps, Kafka consumers, everything. And the peak Kafka throughput that we see is around 80 GB per second. This is all about stream infrastructure at OpenAI, and that brings us to today. Now, the question is, what is the team building right now? Let's go back to the architecture diagram. I promise this is one of the last few times I'll show you this. After some point, there were use cases that needed a lot of ML features, and we were able to extend all of this. So we adopted a system called Chronon, which is basically a higher-level abstraction that enables our users to come up with ML feature, like declaratively define ML features, like how many times this asset is clicked over the last 15 minutes or something like that, and it spins up Flink apps and stuff under the hood. This makes it simple for our users to declare these ML features. So ML feature compiler to manage all of these Flink apps, that is one addition, and we were able to just extend the current architecture. And then we wanted to do real-time data streaming into the data warehouse. That is when we built a system called Streamlink to basically pull data from Kafka and push it into the data warehouse, mainly because we wanted data warehouse ingestion to be more real-time. I'm not going to go into the details of this because there is a talk later today. Adam from the team, he's going to talk about it. I would highly encourage you guys to attend that if you're curious. This is basically stream infrastructure at OpenAI. To just close the talk, I'm just going to summarize all the learnings. So what have we learned through this journey? We learned quite a bit. The first thing is designing for growth early is something that avoids a lot of re-architecture, a lot of iterations, a lot of building things again, thinking from the ground up again, and things like that. So whatever you design, just always keep 10x in mind and whether it scales. The second thing is, this is something that we have learned. We do this learning every quarter. So users will accept trade-offs to use a more powerful, reliable platform. Because most of the problems that our users face is mainly around the friction to adopt and use systems, rather than, oh, I need this particular use case, and that is something that we do not have in infra. So most of the times, it's mostly around usability. So working closely with users and co-building products and solutions with them is a very good start. The third thing is reliability comes from automation and not manual effort. So your initial reliability wins can just come from a nice architecture and a nice rollout, nice engineering behind it. But 6 months, 1 year later, you're going to have so many clusters, so many operational things going on that to sustain that reliability, you need to do something automated, right? And the last thing is getting the right abstractions early avoids a long-term operational toil. If we did not have all of these abstractions, we wouldn't have been able to do a lot of Kafka cluster migrations or maintenances. Now, since the Kafka clusters are not accessible by our users at all, at least they're not accessible directly, it gives infra teams a lot of flexibility to do whatever they want behind the scenes. That summarizes all of the learnings. Let's look at the path ahead of us. I think I've told this multiple times. So many clusters. We need single-click workflows that help us with this. How do you build auto-healing systems? Because as systems scale, there are a lot of problems, a lot of failures that happen. So auto-healing systems are the solution. The second thing is AI-integrated Flink SQL or DSL platform, because Flink does have a learning curve to it, and we also notice that most of the Flink apps in the long term would be something that could be represented through, let's say, Flink SQL or a DSL on top of Flink. So building that abstraction is something top of mind for us. Diskless Kafka, cloud topics, there has been a lot of discussion around this, even today and over the last year or so. So that is something top of mind that we have been thinking about. The last thing is unified ingestion. We've been, even today at OpenAI, ingestion is actually downstream of Kafka. But there are a lot of industry trends on unifying that. How do you prevent the data silos between streaming and data warehouse? So this is also something that we are curious, and it's top of mind for us. That's it. That basically summarizes everything about stream infra at OpenAI. Happy to answer any questions. I don't have the mic here. Oh, maybe the mic is there. Yes, I think there was.
Hey, nice presentation. Thank you. So I have two questions. One was regarding the deduplication that you mentioned, right? So I was wondering, do you usually do that as a service on a downstream Kafka kind of stuff, or do you do that? Probably consumers are more responsible for deduplicating in every service that they have.
That's a good question. So when we went into this, we thought about whether deduplication as a service makes sense, but we wanted to just roll it out without that and see how the use cases shape. Right now, it is more on the service owners, and we noticed most of the service processing logic are idempotent in their own way. Like they either talk to databases or they talk to other systems or do logic that's okay with retries. We do see only a few use cases that end up doing their custom dedupe. If the number of use cases that do that actually increase, it makes sense for us to think about deduplication. But right now, it's all on service owners.
Okay, they're more responsible for those things.
Correct, yes.
Got it. And just a curious thing, do you maintain your own Kafka cluster in general, or do you use cloud provisions or stuff like that, essentially?
We use a mix of all of this.
Okay.
Yeah.
Cool. That's it.
So my only question is related to the controller.
Yes.
So yeah, when we are using the Kafka cluster, so the controller in the back end of some Python scripts are going to be, it will control the brokers and it will write out the last failure of the data and write into the, to pick up the, means to sync up the data. That there, because that is also be leading to the deduplication process and all those. So how you come up with this multi-cluster or so how the Kafka cluster is maintaining in the OpenAI?
That is okay. I'll try to answer that. I didn't understand your question correctly, but I have a few points to add. Feel free to ask it again, like if that is an answer. Okay. So how do we add a new cluster? So with this architecture, it's an FSM of multiple steps. You could call it like let's say a temporal workflow. What we do is we end up adding a new Kafka cluster to. We have this notion of cluster group. So a topic is mapped to a cluster group, and a cluster group is a set of Kafka clusters. So let's say there is a topic that's mapped to 3 clusters, part of a cluster group. Now, if we want to add one more cluster, we end up adding that cluster to this group, but the state of that cluster is going to be consume only. So forwarder is going to connect to that cluster, and it's going to start connecting from the reading from the topic, but the topic will not have any messages. And then once all the consumers connect to it, including Flink apps and stuff, then we move that to, let's say, enable production to it. That way, we do not miss any messages. And this is the process of how we add Kafka clusters. I'm not sure if that answers your question.
Yeah, because nowadays, so the people are giving a wrapped model to avoid these issues. That's the reason I raised this question. Because,
okay.
Yeah.
Okay. Any other questions?
So for your Kafka clients, you mentioned that there are proxies in the middle and
yes.
they're gRPC based.
Yes.
So when these apps connect to Kafka, are they going, the Flink apps, do they go via the gRPC proxy? Because the default clients will directly use the Kafka protocol.
That's a good question. So Flink apps, on the consumption side, they talk, the sources, they talk directly to the Kafka clusters. So Flink apps connect directly to Kafka to consume from Kafka. On the writing side, Flink writes to the proxy. So the read side is basically, so Flink reads from 3 Kafka clusters instead of 1. That's the idea. So if you deploy a Flink app and use the native Flink Kafka source, it directly connects to the Kafka protocol, right? The same thing, just that it does it over 3 clusters or something.
Every app connects to all the clusters, all 3 clusters?
Every app connects to all the clusters where the topic is kind of placed in. So there are, like say there are thousands of topics and over tens of clusters. This topic is mapped to a few set of clusters. The Flink app connects to only them.
And all the functionality that's built into the consumer proxy,
yeah.
Now is that available to in
the Flink
other
apps?
mechanisms to Flink?
No, all the features that is deployed. So think of consumer proxy is more around stateless consumption, where duplicates, all that. So think of that as just message handlers, where every message handler is kind of independent. Anything that is more stateful, Flink directly connects to all the Kafka clusters. It doesn't have any of those like ordering problems and things like that because it natively talks to Kafka. So Flink apps deployments as such doesn't use any of the benefits that forwarder gives you, and it doesn't have the same set of trade-offs that forwarder gives you as well.
Hey, we need to wrap up soon. We just have maybe 1 or 2 more questions.
Sure.
2 questions, quickly.
Yeah.
No, thanks for the talk. A question about the producer proxy. Does the gRPC service then returns immediately or after Kafka acknowledges the message?
Very good question. It blocks unpublish. So, it blocks until all the messages that you give in the input batch is published to Kafka. Otherwise, it does retries and things like that. But a good chunk of use cases at OpenAI do async publishes to Kafka. So on the client side, it's async, and they don't block on it.
Does it mean that there is data loss when the proxy goes down?
Does this mean there is a data loss?
If the proxy goes down before
Oh, yeah, if the proxy is down, yes.
Okay.
But the thing is, the clients block on the publish. So on the client side, there will be retries again, and it will be tried against a different proxy instance. Yes. Okay, one last question. Yeah.
I had just a quick question about your backfill strategies. I think you mentioned you guys are working or thinking about backfills in the future. How are you guys thinking about it? Can you speak a little bit more to it?
Good question. Right now, most of the backfills are served through last half a day or 1 day of data. So we basically reset the consumer to that state, and they just consume. But I think at some point, we would have maybe larger backfills. Maybe it makes sense to write a source that reads directly on top of offline tables and things like that. That's something top of mind for us, but we haven't implemented it.
So what does your Kafka retention period look like? So you're just rewinding offsets?
Our Kafka retention right now is somewhere between 3 to 5 days. Varies a little bit from topic to topic, but most use cases end up are happy with this. Yeah.
Maybe you can catch him during lunch.
Yeah, happy to chat with folks after the talk. We are over time. Thank you, everyone.